Okay. Uh, Good afternoon, dear participants. Today, in the third session of second day of this faculty development program, that is on machine learning and applications in NLP and computer vision, we have a scientist from industry, Mr. Anshul Bawa, which is currently working as a level 4 data scientist for Vedantu, which is a rapidly growing online edtech company that recently joined the Unicorn Club with a valuation of $1 billion. So he specializes in applying natural language processing to make user-friendly conversational interfaces. He holds a dual degree, BTech and MTech in computer science from uh, IIT Delhi. He has research and industry experience, having worked at the Microsoft Research and Interactions LLC prior to joining the Vedantu. Today, Mr. Anshul will talk about applying contextualized natural language understanding to scale. So now I request Mr. Anshul Babaji to please address the audience. Over to you, sir.
Thank you. Thank you so much, sir. Hi, thank you for joining this talk. My name is Anshul, and I am, today I'm going to talk about what I call contextualized machine. Just a second. I think just trying to, okay, great, sorry. Yeah, so the title of my talk is Applying Contextualized Natural Language Understanding at Scale. And this is mostly within the domain of NLP. Some of you have more of a vision background. So you would be familiar with some of the architectures that are used here, like transformers. And but mostly the kind of data, and this talk will focus on text and NLP, and within NLP text. And I'm sure all the other talks here are from reputed faculty members from all over the country. So I wanted to give a slightly different perspective on, instead of focusing on the theory and the rigor behind the models, I wanted to talk about how these days companies are applying a lot of these models and things that we've learned in research, and how they're applied to real world problems. And also, since I also have a research background, I was with Microsoft Research before I moved to completely a data scientist role. So I also have some perspective on what are the differences, like when you're transitioning from a master's degree or a research fellowship into the industry. Then what are the things that that are salient and what are important to note and remember. So I hope that experience, I'm not here to teach you anything. I don't feel I'm an expert in any sense of the word, but I'm just going to share my learnings with you, and I hope you find it useful. So I wanted to break down this title into these different words. So I've broken down this talk into 4 parts. So the title, like applying contextualized NLU, which is natural language understanding at scale. So I'll focus on each of these parts individually, and because these are all different, and they all come together. Okay, great. Sorry, something happened. Okay. Yeah. My screen is still visible, right? Hello?
Hello. Your first slide is visible. AICT Atal FDP 221.
I think someone
Machine learning in applications in NLP and computer vision. So that
Okay.
slide is visible.
Sure. I think I'll just let me get back to change into highlight mode. I'm sorry, I'm not very familiar with the. Okay, great. Now I'm back. Yeah, so let's first quickly talk about what is NLU. I'm sure a lot of you would be familiar with the term, and it's mostly when you're trying to when you give a piece of text or audio to a computer, and you wanted to convert that into some structured representation of meaning, or to extract data knowledge out of it. And um, this comes in the conversational domain, where where the pipeline is that there is some text that comes to the system. It first This is the traditional conversational NLP pipeline. It's called traditional because it's been followed for a long time, even before deep learning became the state of the art in NLP. And this is so it divides the steps of how to respond to a user, or how to interact with the user, into these discrete steps. The first step is NLU, natural language understanding, in which we just take the user's generated text, and we try to understand the intent behind it, or we try to extract the sentiment, or we try to convert it into a structured format. So if you've heard of dependency parsing or semantic role labeling, all these things come under natural language understanding, where you're taking the raw text as the input, and you're trying to embed or impart structure on top of it. Specifically in the case of conversational NLP, what we want from our understanding engine is to identify the intent of the message. So if I let's say you would be familiar with Google Assistant or Alexa, and these voice assistants, and if you say things like if you say wake me up at 6 a.m. or set an alarm for 6 a.m. These two phrases, even though they look different, like they have different words, one of them doesn't even have the word alarm, but both of them mean the same thing in terms of what is the action expected from the system. So the system's action in that case, it will be to set an alarm. That will be the same. So the job of the NLU is to map the input text that was wake me up at time, and convert it into an internal action, which is setting an alarm. So the next step here is the dialogue manager, and this is specific to every conversational application. So if you're using if you're on WhatsApp and you're talking to a business account, and there it is an automated agent that's replying to you, there the logic is completely different. So dialogue manager's role is to convert these input actions or labels to output labels. Like, if this happens, what should be the next step? If the user is asking for some information, it's the dialogue manager's role to fetch that information and present it back here. It's still not gone to the user, but this dialogue manager is separating the conversational part of the interaction from the logical part of the interaction. If you have any questions, you can feel free to stop me at any time and ask. I will try to read the chat also, but I think it's not visible on my screen at the same time while I'm speaking. So please feel free to just unmute yourself and ask questions throughout the talk. And yeah, so this was the dialogue manager. And after the dialogue manager, it's the turn of the what we call NLG, which is the natural language generation step. And what this does is basically like the logic that was returned from the dialogue manager, it is conveyed to the user in the same text format. If the user input was text, then this output will be text. If the user input was speech, then this output will be speech. So in the example that I used of you asking your voice assistant to like set an alarm for you, it will reply with something like, okay, I have set an alarm for you at 6 a.m. something like that. And this again need not be, there's no one correct way of saying the same thing. It could also say something like done, good night, So there are, again, so the intent was to convey that this action has been completed. Now, when it is realized or materialized in text format, this can take several forms. Right. So about NLU, like I mentioned, the most important thing is that the input that is coming in is just a raw string, and the output of the NLU is structured. It could be a classification task. So sentiment analysis is a classification problem. Given a piece of text, we classify it into let's say one of 5 sentiment buckets. It could also be a regression task. We could assign a score to each of these sentiment values. Like if the user's message is of a happy tone, like let's say it's a product review that Amazon 5 out of 5 stars. I am very happy with this vacuum cleaner that I bought. So if we are assigning a sentiment of happy to it, then we can also assign a score with it. Like if we are very confident that this is happy. So all these things that are the output is structured, but the input was just a raw text, which was just the review that the customer had written. Similarly, if it is question answering, then looking at the text and trying to understand what the question is, that is also structured. And this is an example of the logic that goes inside a dialogue manager. So it has different response models that will generate candidate responses. It is internally, the model is generating several responses and evaluating them, whether which of these is most suitable. And it takes inputs from the dialogue history to determine which of these responses is more applicable, and which of these is less applicable. And then it can have some priority ordering that the domain I work in is for Vedantu. What we do is, when we have online lectures for students, which looks a lot like this meeting, that there is one person who's speaking and there's a lot of students who are attending that lecture. And there they ask their doubts in something like this chat panel that you're seeing. And because it's a very large class and the teacher cannot directly answer all of these questions, that is where we put in a conversational agent, or you can call it a chatbot. And there, the role of the chatbot is to answer students' questions. And there we have this kind of a dialogue manager that decides if the student is asking, if it's a lecture for 10th grade mathematics, then the student will have a question like, what is quadratic polynomial? So then I try to identify that this is a definition question, and then we look up in our database if we have the definition for polynomial or quadratic polynomial. And then if there is a response that is, if we have it from a textbook, then we can return it directly. So that was just an example. So it can have, so the candidate responses would look like, one would be the definition of a polynomial. The other would be the definition of a quadratic polynomial, which is, and both of these are fetching the intent from the user message, and both are providing answers. But we see that one of them is more appropriate because it's giving the full answer, because the student asked about a quadratic polynomial. So we want to tell them what a quadratic polynomial is. We don't want to tell them just what a polynomial is. Right. And when the response is selected, it is sent to the generation system, which converts again, because this was an internal representation, it needs to be converted again into a string for the user to read. Or if it is a speech system, then it needs to go into a TTS system. And there are different ways of doing NLG. a lot of the NLG used to be very rule based and template driven, that you have a sentence template and you can put in the variables that are populated at runtime into that template. So the same template can be reused and populated at runtime. Then with deep learning, it's also become possible to generate new sentences uh, on the go, like online. And this requires a lot of optimization from a production point of view, because typically these systems are very slow, and especially training. But training is what we say, it's offline, because while this interaction is happening, you're not training your system. The system has been pre-trained and it is only running in inference mode at this time. But still, when it is an interaction, like the user has typed a message and it's waiting for the system's response. Sometimes if you go to a full deep architecture, and people who have worked in vision would also be familiar with this, that it requires a lot of compute resources to be able to come up with a very appropriate answer. And so that's why in real world applications, it is often a mixture or hybrid of template driven and more advanced NLG. You can also have instead of a generative system, you could also have a retrieval based system, like the example that I just gave of answering this definition, that there can be a database in the backend of uh, keywords, chapter specific keywords like polynomial, quadratic polynomial, etc., and their definitions. And at runtime, all you do is retrieve them. So it is a matching, retrieval or matching task that the model has to decide which of these definitions is the most appropriate. And this is, I am talking about dialogue systems, but text generation or NLG has applications in a lot of other places as well. For example, machine translation. A lot of the architectures that are currently used for dialogue systems actually came from machine translation. And this is a lot more well-studied problem, and it used to be done completely statistically, like statistical machine translation. And then there was a neural way of doing this, neural machine translation. And a lot of those principles and architectures are also used within dialogue systems. Other examples include text comprehension, text summarization. So given a very long article or paragraph, to be able to um, uh, condense it into a smaller, concise piece of text. And within text summarization, there is extractive text summarization and abstractive text summarization. And you would need to generate new text in the second kind, which is the abstractive kind. So given, let's say the task is given a full research paper, write the abstract of that paper. That would be a task that comes under abstractive text summarization. And dialogue systems also are can be of two kinds, whether they are very specific to one particular goal. So, for example, if it is a bot that is designed to take orders for pizza delivery, it's a bot that Domino's uses or Swiggy or Zomato uses. Then it would have a very specific goal. Then another kind of dialogue system would be that open domain, which is a better example here would be Cortana or Google Assistant or Siri and Alexa, because they are also designed to answer chit chat kind of questions. You can ask things like, how are you? What are you? What is the time? What is the weather? So it's not specific to one goal. It is open domain. So, and because of this difference, the design of these two kinds of dialogue systems ends up being very, very different. Okay. Any questions so far? All right, I'll move on. So yeah, what I just talked about was the traditional NLP pipeline, which is in which we had these slightly discrete components of like an NLU and an NLG and dialogue manager. While that structure is still followed in a functional sense, but in terms of the models, a lot of the state-of-the-art models these days are they follow the encoder-decoder architecture, and in this case, um, there is no intermediate representation. Like I had mentioned that um, the NLU would convert the text into intents, and here there's no machine representation of the intent per se. What it is learned as is the different weights inside a neural model, which is can be the encoder or could be the decoder, and here these words are converted to their vector representations, which is multidimensional. Usually it is around 300. Um, and and so this architecture, encoder decoder, this also came from the machine translation domain, where what they would do is they would take inputs as tokens from one language. They would let's say they would take inputs from French, and the output would be trained to be English, the translation of that. And then this design, the same architecture was used for, instead of uh, translation pairs, it was used on question answer pairs or query response pairs. So for example, if a message is, the input message is how are you, the system is trained to reply I am good. And this is similar to, if you're familiar with recurrent neural networks, that these are different time steps. So this is the same encoder that is getting these inputs at different times, and it is incorporating the previous inputs in its current representation. So at this stage, let's say, sorry, yeah, at this stage, it has whatever the intermediate representation is. It includes everything that has come before it. And once it sees a question mark, it knows that the sentence has ended. So all these things, this kind of an architecture is able to figure out because it is being trained on a lot of these question answer pairs. Like the volume of data that these models need to be trained on is orders of magnitude higher than traditional systems require. That is because everything about the data is being learned by the model from examples. We don't tell this model what is proper English, what is improper English. So all these things the model figures out from examples. And that's because each of these words are converted to their vector representations. And uh, by repeatedly doing this for correct training pairs, the model's weights, and based on whatever loss functions are used, the model's weights are trained to be able to replicate this behavior as closely as possible. And similar to sequence models, nowadays the state of the art is what we call transformers, and they can do a lot more than just decoding and replying. They can also be used for classification and sentence completion. And so the input output behavior it's a generalization of the standard sequence to sequence model. The input is still a sequence. Transformers, so this is an example of a transformer architecture. If you look at this green outer box, it is an encoder. So it is similar in design to the sequence to sequence models, but it is it goes deeper into, so there can be multiple encoders, there can be multiple encodings of the same message, and the output is customizable. You can change the last few layers, and you can fine tune it for any kind of an output that you want. So if you want to do something like semantic role labeling, then your outputs can be different semantic roles. If you want to do named entity recognition, then you can change the outputs to named entities, or whether or not this word is an entity. And if it is an entity, then what kind of an entity? If you can also use this for any task that you can think of. For example, it could also be language identification. So given a sentence and you don't know which language it is from, it could also be that half of the sentence is in English and half of it is in Punjabi. And even in that case, you can do it at a token by token level. For every token, you're able to tell what is the language of that token. And so basically, the keeping the architecture as the same, the architecture serves to um, learn a representation of the data, and that is most conducive to your task. And when we say no intermediate representations, what we actually mean is no explicit intermediate representations. That we don't need to sit down and come up with a structure of language, for example. What it is learned in terms of these weights, or that give at every step of the decoding, we know a probability distribution over the entire vocabulary. And at runtime, the model is just asked to find, okay, given that the one word that I generated was I, like in this I, what the next most probable word is am. And after am has been generated, the next most probable word is good. And this is what the model has learned. And therefore, at runtime, it can generate these sentences. Okay, so this concludes the first part, which is the natural language understanding aspect of it. Moving on to the second, which is what is the how is applying this different from the theory of it. And that brings me to the difference between what I would call well-behaved data and user-generated data. So mostly user-generated data has, it comes predominantly from the social media domain, where it could be people's Facebook posts, comments. It could also be WhatsApp messages, and it could be emails. But mostly it is more open domain, where either the audience is uh, uh, other people, like it is in a broadcast form, in terms of let's say WhatsApp status or Facebook post, or it is between two people or a smaller group of people, like DMs or private messages. And a lot of the models that are built in NLP have to be changed and customized to be able to work with this kind of data. It's no longer the case that we can still use models that were designed for, let's say, newspaper articles, or transcripts of public speeches. So all these data are a lot more. So these are what I call more well-behaved data, in which we understand the characteristics of the data very well. So if for those of you who would have worked in NLP, you would be familiar with a lot of these standard data sets, like the WSJ corpus, for example. And there it is mostly all of this text has been written carefully by newspaper editors who are all well trained and experienced, and they all come from the same country, which Wall Street is the United States. It's an American newspaper, so they all speak a very standard form of English, and it is they write their sentences in print medium, so it follows grammatical rules. You wouldn't find half-formed sentences there, for example. And all of this makes it very I wouldn't say very easy, because but it is a different kind of domain in which you have a lot more guarantees about what the data can look like. And in the context of implementing, like if you build a language model uh, trained on this data. A language model is when you teach how to form these sentences to a computer. Then that model will have very low perplexity, which means it will not have a lot of uncertainty compared to the next kind of data that I would come to. And even within these NLP applications that I had mentioned, that kind of tasks that can be done. So, for example, NLU, we could have done a full constituency parse or dependency parse of these sentences, because there is a very well trained Stanford dependency parser available, or there's a lot of resources available for, let's say, English, and those can be used directly if you know that your data is well behaved. But as soon as you come to uh, or you can do relation extraction, and you can get very deep parsing instead of very shallow surface level information, um, and you can convert it to a very structured representation. But when it comes to user generated data, if you look at, let's say, your own WhatsApp messages that are sent, even if you're using all these Roman 26 alphabets, you might still be typing in Hindi or Punjabi or whatever your native language is, and your recipient will understand it. And but it will be, if you just give those kinds of messages to a computer, it doesn't know what those words mean. So how does it figure those things out, right? So, and language is like, mixing of language is just one feature of user generated data. There's all sorts of, you can split one sentence into several messages. You may not even put full stops, or and your intent will still be understood. And you might use abbreviations. You might put a lot of emojis. You might put images with text. And all these things are features of this data. It's even when we say that we are cleaning our data, and if we end up removing all of these things, then we are losing a lot of the information. And because a lot of it's generated in a very decentralized manner, like anybody with a phone or with a keyboard can generate this data. And it can be, so like, for example, for this meeting, if there is a chatbot, then all the participants can be typing at the same time, and the system will still be responding to all of them if it's working. And so it is characterized by a very high volume and high velocity, which is, by design, it was not a feature of more well-behaved data, because it was generated by a smaller set of people, and who would follow rules a lot more. So there was more uh, thought put into creation of that data, for example. And yeah, so the features of this kind of data would be that a lot of the meaning is ambiguous. So, for example, yeah, if the two different people can say the same thing in a different manner, everybody will have their own way of saying thing. And you can just put, let's say, you can just put a question mark, and the implication is that you didn't understand what was said before. So the same token, the question mark, based on whether it comes at the end of a sentence or whether it's present just as an independent message, or if it was, let's say, one question mark versus three question marks. If you put three question marks, then you want to indicate that you're very confused, for example. So, and all these things are like features of real world data, and the vocabulary itself keeps evolving. There would be words that were not a part of a vocabulary 10 years ago, but now they are used commonly in social media. And for example, for SMS, people, because there was a limit on the number of characters, people ended up using so many contractions and abbreviations. And usage of words goes beyond their semantics. So, for example, let's say LOL, which means laughing out loud, based on where it comes in a sentence, it could actually mean that you find something funny, or it could also mean that you are trying to say something a little more politely or less aggressively. So so the usage goes beyond the semantics. So it's not enough to say that these tokens individually mean this thing, therefore the full sentence will mean what is the sum of its tokens. So the compositional meaning can go beyond semantics. And there is often multi-party dialogue as well. Given a message in a chat room, or even in this chat from in this meeting, um, it is a task for the system to identify who is it addressed to. Like if there are 200 attendees present in a meeting, and if somebody has typed something, are they addressing everybody? Are they addressing the speaker? Are they just are they not addressing anyone in particular, or are they replying to a previous message? All those things are not labeled directly, and there have to be indirect ways for the system to figure out these things. Language mixing is something I've already talked about, that there can be words from different languages in the same message. And it could also be that one person is talking in English, the other person is talking in Punjabi, and they can understand each other, but they are still using different languages. But if the system is not trained to even recognize Punjabi words or any non-English words, then it won't get the full meaning in the conversation. Then there is a lot of non-text context. So like I mentioned, in WhatsApp, we don't just use text. We use a lot of emojis. Some people use stickers. Some people use images, videos, GIFs, and that is all part of the context of one conversation. So whenever anybody is using NLP, their first hunch or tendency would be to make a model that ignores every other form of data and only makes a text-based system, which is perfectly reasonable as a first step, because you want to be able to first at least get a handle of the text before you move on to other things. But this context, after one point, it becomes crucial to understanding what a student is talking about. So, for example, for Vedantu, how it happens is, again, like I'll take the example of maths lecture. There is a question that is x square plus y square equal to 4x minus 3y plus whatever. And the student is asking, sir, how did you get the value of x? And if a bot has to answer that question, the bot needs to figure out what is the x that the student is talking about. Where is this x coming from? It could be a standard formula. It could be like x plus y whole square equals x square plus 2xy plus y square. Then that is a different kind of x. If there was a question on the screen which is like find the value of y, and for that you need to find the value of x, then it is a different context. So what was on the slide at that time, what was the teacher saying at that time, what is the lecture about, all those things are important context just to identify the intent behind this one simple sounding message, which is how did you get the value of x. And the same question can be asked in the beginning of the lecture or at the end of the lecture, and the meaning of the question will completely change. And we cannot just only use the text of the message to be able to answer it. And this is again a feature across all user generated data. That is, it's not specific to the example that I just gave. Even on even in let's say in a group conversation like WhatsApp, who is sending that message? Are they replying to somebody else's image that they've sent? All those things are important. These are what the model is trying to figure out, what was the intent based on non-text features. So context, the word itself is like, if you look at con plus text, so everything that comes with text, that is not text. That is what we mean here specifically by context. Then again, because spam, like I mentioned, this data is very this data has a very high volume and high um, velocity. It's also that the not everything that is mentioned in a conversation will be relevant. So based on whatever task you're trying to achieve, there will be messages that are relevant, and there will be messages that are irrelevant. So spam is a category of like removing any this kind of irrelevant messages from your domain. And again, the definition of spam varies. For email, spam is any email that you do not want to receive, and it could be you do not want to receive it because it was sent to like hundreds of people at the same time. It is not addressed to you specifically. Or it could be that it is sent repeatedly. Like it could be that you subscribe to some website, but then slowly they send, instead of sending you a monthly email, they send you 5 emails every day. And even though this is relevant to you, but it is very repetitive. So this is also spam. So there are different kinds of spam that also would come in different domains. And this is again a salient feature of any user generated data. There could be profanity, there could be URL links that could be sent by a scammer, that are sent to uh, um, any Facebook group, for example. And there's a lot of effort that these companies put in to make sure that spam is prevented as much as possible. And finally, there is a concern for privacy, that all the data that is generated, it is not in all of these cases, it is not always owned by uh, the platform or the people. And this is a very evolving landscape. So for example, for WhatsApp, you would have heard of this feature called end-to-end encryption, right? And so that means that, okay, I am audible to everyone, right? Could you
You are.
type it? Okay, great.
Yes.
Thank you. Great. Yeah, so privacy is a big concern in because this is all user-generated data, and people don't want it to be somebody else to buy this data or use it to target advertisements. And has anybody here heard of something called GDPR? GDPR. Yes, lovely. There are some people who have heard of it. So GDPR is a regulation that was introduced in the West, in the European Union. It stands for General Data Protection. Yeah, yeah. So I'm not sure of the acronym, but it has a lot of implications on how different anybody who's using data, even if it is for research purposes, even if a research scholar is scraping that data from the web, they still need to be if you submit your paper based on that data, and there will be an ethics review committee, or the IRB panel. That is when they're reviewing the paper, they will look for whether or not you are following GDPR recommendations if you send it to any European conference or journal, for example. And what it does is, one of the features there is that any user should be uh, yeah, so how to check for GDPR? If you're applying to a conference, you can they would, in their review process, they would mention it, like if they're what is their process, and the reviewers would maybe ask for those kind of things. So when you're providing the link to your data, for example, they want to make sure that you are decoupling what is called PII. PII is personally identifiable information. So if you've taken data from somebody and you have their email ID with you, then you should store your all this personal data like email ID in a separate database from where you store all the other data, which is let's say the email sent by that person. So given any data, you should not have. Yes, thank you, Vishal, sir. General Data Protection Regulation, yes. So it was only implemented within European Union, but slowly it's becoming, because any company that is working in the EU will also be, will try to make systems for them, and it slowly becomes global. So a lot of the regulations first come from a particular geography, and then they become more generic and applied globally. So it's still important for everybody to at least know what this is, even if it does not directly affect you. But wherever you are getting your data from, there would be let's say it could be Reddit, or if it is open domain, then you would have to look for the license that is applicable. It could be GPL, General Public License. It could be Creative Commons. It could be you might have to ask the website. You might have to look for these things if you don't want to breach any privacy concerns. So one thing that happens is one way it affects your let's say your model design would be that you need to keep your data indexed at all times. Indexed would be that you need to have some like whenever you're storing it in a database, you would have an index, right? And if you are training a model, and your model is trained on a few strings, then I should be able to use the index to say that, oh, this particular user wants to remove their data from my model. That is a right that the user has thanks to GDPR. And at any point, even if you have trained a model, even if you're not directly using that data, but because you've trained a model, it should be possible to remove that data and to still have a trained model. And to be able to remove that data, like once a model is trained, and now if I ask you, remove all the data that was generated by this user, but now that it's already trained, so it's in the weights of the model. So what you need to do is to identify the index. Like if you have an index of like which were the data points that were uh, that came from this particular user, it's only then that you'll be able to diagnose that within the system and go in there and take it out and make sure the rest of the model still works. Otherwise, if it's completely black box, if you've discarded that column in your process somewhere, and now you don't know which of these messages came from which user, for example, then you won't be able to meet these kind of regulations. So because of these privacy concerns and this kind of issues, this again is like it's not just it's a inbuilt inherent feature of real world data. It's not something that you can ignore going forward. Yeah. We get to the next slide. Yeah. And yeah, so because of all these different features, the way we process our data in any model has also changed significantly and evolved basically. For example, if you would have heard of things like stemming and lemmatization within NLP, these are the standard pre-processing steps, right? Um, and nowadays you would see that it's very it's not very commonly used. That's because again we don't always so lemmatization and stemming works when you try to identify the word root, and if your language itself is so heterogeneous and uncertain, then you need to preserve all the whole token itself. You cannot afford to lose uh, parts of the token to in this format, and you cannot run with this assumption that you will know the entire vocabulary beforehand. And if you get a sentence that has a lot of out of vocabulary words, it should not throw an error, and the model should have like a what would you call a best effort uh, uh, process, you know. So it tries to find out as much as it can about the model without worrying about the things that it does not understand. So this is again a design principle that comes in. So instead of stemming and lemmatization, what we would have is what we can be normalization, which is similar to um, lemmatization, but it's done in a different way. For example, if somebody types kya, KYAA, and someone else types kya as KYA, and both of these are they are the same word. There is difference in spelling because it's not the standard script. Like, it's not being written in Devanagari, it's being written in romanized script, in the Latin alphabet, and that causes these spelling issues. So when you normalize, you can take care of converting all of these into one form. Or for example, if there's thanks or ty and thanks space u, they can all be converted to one form. And all this comes under normalization. And these are again broadly standard pre-processing steps that are followed independent of what the problem is. Any NLP pipeline will have some version of this, and linguistic cleanup again, removing correcting for spelling mistakes, for example. There are a lot of spelling mistakes on user generated data, and every out of vocabulary word need not be just a spelling mistake. It could be an actual new word that your system does not recognize. It could be a spelling variation of a word that you do recognize. So all these things, handling all of this or rejecting all of this, comes under the pre-processing. And here again, you need to, based on what your problem formulation is, you might want to remove some words, what are called stop words, preemptively. If you know that, so for example, in one of the messages that is sent here, like somebody would said no sir. In that, the intent is actually just the first word. The second word is just addressing uh, the person who's speaking, in this case me. So the word sir can be considered a stop word when it comes to intent identification. If your problem is different, if you're also trying to identify who is it addressed to, then the second word is more important. So you what counts as a stop word is not a standard definition anymore. Now it depends on what your problem formulation is. Deduplication again, or spam removal. One very common kind of spam is repeated messages, that I just copy something and I just paste enter, put it in the chat, and like flood the chats or something like that. Those kinds of data points can, if your data has that, and if you haven't had a look at your data, you're just downloading it and training a model on it, then it would get biased towards that kind of spam. So you have to find out ways to identify it and remove it. And one way of doing it is deduplication. Indexing I'd already mentioned, which was that every data point that comes from, it needs to be linked to all the metadata that is attached to that. Like who sent it, at what time did they send it, what was, how many students were in the class, for example. Timestamp. Twitter would have something like geotags, which is when this tweet was sent out, where was the person located. Images also have this metadata. So all these things are useful when it comes to. Kindly repeat normalization. Sure. So normalization, instead of using the words stemming and lemmatization, I used the word normalization here because it is a more general form of. So have you, if you look at what is tokenization, right? So you take a full string and you convert it into discrete tokens. So those tokens can be, the individual token can have spelling variations, can have different forms. It could be, let's say somebody just typed TYSM without any spaces, and you don't have an explicit model of what this word means. But from your analysis, you have found that, let's say, when it is represented, it is used in the same context as whenever thank you is mentioned. So if you cluster it, you'll find that these all words are functionally the same, like they have the same semantics. So you can, in your model, you can actually change these to the same format. You can normalize this into one representation, and you can put it in your pre-processing itself. So wherever there is, let's say, TYSM in the data, you can expand it to the non-abbreviated form, which is thank you very much. Right. And so yeah, like this pre-processing, there are some parts of this pre-processing that are standard and can apply to a lot of, and these are also what you would find mostly in a lot of textbooks, because these are, this comes as a part of standard good practices. But there would also be a lot of processing and pre-processing that you need to do that would be specific to your problem formulation. So given any data, you need to define for yourself what is the noise and what is the signal. Like what is the information that you're looking for and what is it that is irrelevant for you. So if I'm trying to make a system that can answer questions that people are asking in the chat panel, then anybody who's not asking a question is I don't need to do anything for that, right? So in that case, for that particular problem, questions are signal and everything else is noise. If I am trying to build a system that is, again, it is a chat system, but it is trying to, it is asking quiz questions, like while I'm speaking, after every 10 minutes or so, it asks a simple quiz question and everybody answers that. Then the system is actually looking for answers and not for questions. So the signal changes. Now what was signal now becomes noise. So based on what the exact requirement is, you need to be able to differentiate signal from noise. And again, you cannot identify everything that is there. Or even if it is a longer message, if somebody has asked a question, they can say a bigger sentence like, I am not following anything. The speaker is not speaking loudly at all. Please explain this again. So within this full message, just this part of please explain again is what the system would probably want to recognize. And it would also be the easiest to understand because it is stated clearly. So that would be the lowest hanging fruit. Like it's the easiest to build a solution for. Everything else will need a more complicated solution. So instead of trying to incorporate all the edge cases in your model and making a lot of complex rules in the first iteration itself, uh, it is a lot more easier to just have a very simple model that works with the lowest hanging fruit, which is least effort needed to get the most results. Start with that and then move on to the next lowest hanging fruit. That once you've addressed all the simplest of messages, like even in this chat you can see that a lot of the messages would be yes, no, okay, thank you, which can come under greeting or small talk category. And these would be the what I would call the lowest hanging fruit in this case, that answering or being able to understand these messages solves, by data volume, it solves 40-50% of your problem, right? And if you have any questions about whether or not this is relevant or irrelevant, you have noise or signal, then you can actually also validate your hypothesis. You think that, let's say, you're confused whether or not you should remove emojis, um, or emoticons. And you see that if you remove emoticons, there's a lot of messages that are just empty or they don't make a lot of sense. So you can actually test this, like while removing and without removing, if there is a correlation of the presence of an emoticon with something that you're looking for. For example, for sentiment, then it's slightly obvious that emojis will be useful for understanding sentiment. But even for other tasks, whether or not a student is serious or paying attention or talking about something relevant to the lecture or irrelevant to the lecture, all these things also you can infer from just the simple fact that whether an emoticon was present or not. So you can start with a simple feature, which is, let's say, just a binary feature: yes emoji, no emoji, right? And you see whether it is useful for your model. Does it have a correlation with your output variable? Removing it, does it reduce your confidence significantly? So all these things also would come under data processing, or I mean, I would actually call it pre-processing, because you're you're rapidly testing what is a useful feature in the input raw data itself. And once you know that it is useful, let's say you find that presence and absence of emoticon, which is just a binary variable, this is useful. Now you want to refine, so this iterative refinement of feature granularity. Now you want to know more about this feature. You want to convert it into a multi-label feature. Like I am not just interested in whether or not an emoticon was present. I also need the next step would be like a bag of words model. I also need the vocabulary, which emoticons were present and how many of them were present. Then I can also ask for what position were they present in. Were they at the beginning of the message, or in the middle of the message, or at the end of the message? So based on what the depth of your requirement is, you would have to change the way you formulate your feature. And this problem formulation itself is uh, is best done as an iterative process. That once you find some results, even if they're negative results, there will be a lot of negative results when you're trying to find out what is relevant. And once you find a feature that you find is important, then you can make it even more granular. Okay, so I think we can take about a 10 to 15-minute break because there's just a small part that's left. And I've been speaking for a long time. I think it will be better for everyone's attention that we can reconvene at, thank you, Vishal sir. Let's come back here at 3:55, which is 15 minutes from now. Yes, I'll type my email ID here. I'll type my email ID in the chat. Somebody asked for it. All right. I'll resume at 3:55. Share my screen again. Okay. Great. So let's resume. Uh, right. So we have talked about like what is the difference between like the theory of NLP and applying NLP to specific user-generated data. And now I wanted to quickly just talk about the other two issues. One is I've already touched upon this a little before. The first is context, which is um, all the non-text data that is useful. Yeah, so I think I'll finish in about this in about 10 minutes, and then I'll show a demo of how we've done things at Vedantu, which is you'll see the examples of all these things that I've talked about. It's a short video, and then we can have some questions. So yeah, context, like I mentioned, it's you know the word is a lot of the times we say that everything that's just not within the bounds of the what is modeled is called context, but like so we're trying to make it slightly more specific. Like everything that is not modeled, if it's context, then even things that are not relevant are context, right? So only the most salient parts that are needed to understand data. So here is one example of so in linguistics, there are things like semantics, syntax, and then there's pragmatics. So one very classical example of where pragmatics comes into the picture is, let's say, if there are three objects in front of me, three people I'm talking about, and I have to refer to one of them. I have to uh, describe them as, oh, I'm talking about this person, and I need to use a referring expression for them. And there is a now it's like that each of these have their own features. All of them have two eyes, all of them are smiling, and two of them have glasses, one of them has a hat. So if I say that I'm talking about the person wearing glasses, you know, then logically you don't know which of these two people I'm talking about. It could be the person in the middle, or it could be the person on the right, because both are wearing glasses. But it's like if you had to pick one, which one would you pick? Like if I'm telling you that I'm talking about the person with the glasses, would you pick the one on the left or the one on the right? No, sorry, one in the middle or one on the right? Anyone? Middle. Yes. Right, exactly. Because so pragmatically, if you think of it like if I was thinking about the person on the right, then I would have said hat, because that's the most obvious thing to say for that person. But because I did not say hat, I that means I'm probably not talking about the person on the right. I'm talking about the one in the middle. And this is so what I just did, this reasoning that had I have talked about that person, then I would have said something else. This is like a counterfactual reasoning. And this is like, it is in the space of possibility. It's not that there was another message in the conversation somewhere that was about, you don't, that hasn't even happened, but you're still doing this reasoning. And that is, you have one piece of text, which is what I said, which is the person with glasses. And the reasoning that you're doing, uh, this is also would come under context, because this is information or deduction that you're doing that is beyond what is said. You also are thinking about why something else was not said. Does that make sense? So this is one very important thing that comes in when you're modeling context. So, for example, let's say whenever in this conversation, when you are looking for, what the referring expression is going to be, the person with glasses, you have somewhere in the context that there are only three possible people I will be referring to. So you have limited the space of things that can be linked to the text. So the text has an expression, which is a referring expression, and there are three possible referents, which are the different objects or people that can be referred to within the conversation. And yeah, so this is one kind of context. The other kind is, people who work in computer vision would be familiar with tasks like image-based question answering or image captioning. So in this case, there is both a vision uh, uh, component and an NLP component. There is a neural architecture that is, this CNNs are most commonly used, that takes the image as the input, and that becomes the context. So if someone is asking, where is the giraffe? Uh, if you only just get this message, then you don't know the answer, right? Even if you understand the intent, you cannot take any action with that intent, because you don't know any other details about the referent. The giraffe is the referent. But if you have the image, then your CNN can tell you its relative place with respect to other objects. So if you segment that image and you identify that, oh, there is a tree, there is a giraffe, there is a French, there is a fence, and there is a person. There is a lady who's looking at the giraffe. Yeah. So uh, all this information is only coming from the image. So you need both of these things together to be able to answer the question. And your answer can be, either it can be in front of the tree, or it can be behind the fence, or it can be facing the person. So all these are information that you have gathered from the image, which is again the non-text context. So what do these context features look like? Um, so at any given point of time, let's say if it's a full conversation that's going on, whenever an input comes in, what were the current discourse referents that were happening? So it could be like, for this slide, if someone asks, please explain this again. Now, how do I know what does that person mean? So when I read that message was sent at 4:03 p.m. and at 4:03 p.m. I was on the previous slide. So if somebody asked, please explain this again, then I would have to explain whatever I explained at this slide. So this becomes the context of this message. So all the things that can be referred to, the example I'd given earlier, which was X. What is X? So that value of X would be different for different slides, right? And so whatever is the latest referent that can be uh, referred to using the referring expression, that is something that we need to keep in the model. This is also similar to a slightly more standard NLP problem, which would be anaphora resolution. Or um, has anybody heard of anaphora resolution? So if in a long paragraph you have pronouns, you have his, her, him, they, right? So, and there was somebody else who was mentioned, like, yes, pronoun resolution, exactly. So pronouns are one kind of anaphora. Then this, that, these kind of words can also be anaphora. The person, the author, all these are also anaphora. So whenever there is any expression that is trying to talk about either something that was mentioned in the same conversation before, in the same text, or it can be non-text as well. Then what is also important is who is being addressed in a message. Now, again, if I find words like sir in a message, then it's probably directed at me because nobody else is speaking right now. And if multiple people in a conversation, then either one of them would be tagged or one of them would be replied to. All these features are important in being able to convert one stream of chat into what we can call a conversation. It's not a conversation if you don't know who is talking to whom and who is replying to whom. And again, you take time aligned inputs from other modalities, that both of these. So modality is something like text is one modality, speech is one modality, video is one modality, right? So you have inputs in these different formats. They are encoded differently. They have different data signals. One of them is time series, one of them is discretized and tokenized, but they are all part of the same conversation. And then you need to, when you're taking all these inputs, you align them with time. So at any given point of time, you align all these together, and then you look for uh, the 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 neighborhood. Like you can take a window of time that you think is relevant. So at any given point of time, whatever was said in the last, let's say 10 seconds was relevant. You can start modeling with this assumption. If you feel that this is not capturing your context, you can try increasing the time window. If you feel that the context is too ambiguous or too noisy, you can try reducing this time window. So all these things are very ad hoc. There's no principled way of knowing what is a good context. Of course, it can be, you can have some theories like, human working memory has an average duration of 15 seconds, for example. You can have this from psychology. You can use this as a starting point, but your model may not have the same behavior as the predicted theoretical NEAT standard. So that's why you need to be able to have these kind of variations. Like just put it as a parameter, and you can vary the exact measurement of this parameter through things like grid search or parameter optimization. And your metadata can also be at different granularities. So it could be specific to the person who's speaking right now. It could be about have these two people interacted before? Was there a lecture that this person has attended, or is this the first lecture that this student is attending? If you have taken exams or quizzes before, what is the so in a physical actual classroom setting, if a teacher knows the students, then they would also remember things like, oh, this person had a very good grade in the previous semester, or they usually do very well in my subject, but today they're not understanding something. This is also useful information, that whenever you're answering a question, you take this into account and you decide what the answer is based on these features. So at least in the encoding of your data, you should have this somewhere, that this feature may or may not be useful, and you can let the model see if it is, just gives it as an input to your model, something like the encoder decoder, and let the model see if that feature is salient or not. And similarly, you can explicitly label events in the timeline. There could be non-text events that are happening. Let's say uh, there was a conversation you're looking at, and that there was a news in around that time, and people are talking about that event. So you can triangulate that from the date or from the time. that if somebody is talking about Diwali, if somebody mentions Happy Diwali, if they're doing this around October and November, that means they're actually talking about, they're actually greeting, or like it's a greeting. If that word comes in some other context, if it comes, if the word comes in around February or March, then you know that they're not talking about the present, they're referring to something else. So this kind of context, this is one example of how events can be useful. This might be, yeah. I think now it's a good time to. Okay, there's just one more slide left. For scale, I'm just going to just brush through it. So what at scale, what it usually means is like in research settings, or when we are, let's say when we're writing a paper or for benchmarking a model, what we do is we implement a POC. It's a proof of concept that this is how we have modeled our problem. These are our assumptions, and this is how we believe the model will work, and this is our test data, this is our training data, right? So this is what I'm calling a proof of concept, that you have shown that the idea, your model improves over other models in this slightly controlled setting. Now, um, uh, for an industrial application, there's also would be you would, if you have a proof of concept, if you have a trained model, you would want to send it to, let's say, the engineers, or you want to put it into production, it's called, like, so that the actual users of your system are able to use that, and that's production. So from POC to prod, and there are a lot of things that happen at that stage that actually affect again your the way you formulate your problem, and which research problems are prioritized, or which get more funding and things like that. The first step was obviously contextualizing to the user expectation and product requirement. So if it is in the chat domain, one very important constraint is latency, that your system should be able to reply in a time that is realistic for a human, like for a human to be typing. If your system takes 2 minutes to reply to a given message, that's probably too much, because nobody will wait that much if they're in this kind of a setting, if they're in an online meeting, whereas if it is just like product review analysis, then latency is not an important concern, even though you're still dealing with data at scale. All the other problems are there, like contextualized natural language understanding at scale, and it is applied, but your product requirement is completely different. So in that case, you can afford to have a lot more heavy model that is trained on a lot more data. And also, so one thing that we tend to do in research is optimize on accuracy, and that's obviously great. I mean, obviously your model is supposed to be as accurate as possible, but there will be trade-offs with other considerations, like if I have a very simple rule-based model that gives me 79% accuracy, and if I have a state-of-the-art transformer model that gives me 81% accuracy, right? And my I was asked to make something that was, at least 80% accurate. So now technically I should be using the one that is 81% accurate, right? But I might have to take this judgment call that the system, the more expensive system, like, because it is doing a lot more computation, and it's not running on my system. It will be something like a GPU, or it could be something on AWS or Google Cloud, right? So there will be costs associated with that, and in the end, they might do some financial analysis and say that, oh no, you're not saving as much money by doing this much, by adding this extra 2%. Um, and so in that case, the 79% model wins because it's not it's faster, it's easier, it's also going to be easier for a programmer, like somebody else is working on it for them to understand what this model is doing. If I make a black box model that is not interpretable, that becomes really hard as a if you think of software engineering principles, basics of that you should be able to document your code better, you should be able to know modularize it well. All those things become harder if you use very opaque models. A lot of these deep models, I'd shown you the transformer architecture, you saw how many layers it had, right? So it comes at a cost. Like where is that? Okay. Uh, okay, can't find it. Yeah, this. So you're doing a lot of normalization steps. So you are encoding a lot of information. Your model is learning a lot, right? But it is called black box because once it has learned all these things, you don't know which component and which weight. So there's a lot of neurons. You see, each of these feed forward blocks is actually a feed forward neural network, and there is an attention layer which is assigning weights to different input tokens and learning this. So there's a lot of biases and weights that are added, and each of these the neurons themselves go into millions and billions. And that's why they're like the ones that are available in production, like there's very few companies that have these kind of resources to be able to provide those. So if you're using them out of the box, it's a lot easier to use a pre-trained model for yourself. But if you have to train it for yourself, or if you have to fine tune it, then you need different kinds of resources. And this is not an industry specific problem, right? It could also be that what is the GPU that you have available in your own lab, and what are the software that are supported, and is if you're using a CUDA based library, for example, then you need GPUs that support that. Otherwise, you can optimize your code for CPU, but it won't be optimized for GPU. All these kind of concerns come in that part of it. Right. And it's also important to have, a way to incorporate feedback from the users. Like I mentioned, you can't predict all the variables beforehand. And what will happen is, you're training on data that did not have your model. And then you put a model into production. And that model itself will change the user behavior quite a bit. Now, users may not have seen a bot before. They were used to a human answering them. Now there's an automated system. So will they talk to it differently? Like when people give voice instructions to their phones, is it exactly the same as talking to another person, or they try to modify their behavior based on whatever they understand of the system, right? Those things also it's what is called a double order chaotic system, that the introduction of the feature, like you had done some training and now that training data itself is not applicable. So you have to do an iterative process here again. And you need to be able to learn new things without forgetting old things, right? So a big problem with neural networks is what is called catastrophic forgetting. And this comes under, you might come across this in a machine learning course, what is active learning, which is given individual examples, that these training examples I want the model to change its output for. If I give it that feedback, it might also change the what it has learned about other data points. And we don't want it to forget the good things while we are teaching it new important information. So there's a trade-off there of how much you can relearn with the same data. Right. And okay, so enough of one-way lecturing. I'll just quickly show a demo of some basic implementation of these things, and then I'll leave it open for questions. I have to share a different window for that. Stop sharing. Okay, let me know in the chat if you cannot hear the audio here. Okay. So here are some of the things we've been able to do with Vigyan so far. We can answer simple academic questions, and when the system has several questions that are similar, they can ask the student if it's one of these questions that they're asking, and they can select the answer if they like it. They can go through the options. If they don't like it, they can forward it to CP if their doubt is not resolved. And when things get forwarded to the CT, they can see the whole message context and look at where the student is stuck at. So the simple questions get handled automatically, and more complex ones get forwarded to the CT, and then they can resolve it from their end. Then the other kind of messages that we can handle is common non-academic messages like tech issues. So here's an example, like the audio or video or internet might be acting up, and so we have templatized, regularized flows for handling each of these. The first thing would be to refresh. If that doesn't work, then something like logging out and logging in. If they're still facing issues, then they can reach out to a toll-free number or an email address. So we have built in that kind of an escalation matrix that we can also update. Finally, we can handle simple slide context questions in which there's a question on the screen and the student is answering one of the options, and then looking for an explanation of why the correct answer is correct, things like that. Thank you. Right. So, was it audible? Should I play that again, just to make sure? Because I think I was speaking a little fast in that, and so basically the context there was it was like a live class that happens within the Vedantu platform, and okay, it was audible. And CT is the class teacher. So whenever a student is attending a lecture, you saw there was a chat panel on the right side where they can also ask questions while the lecture is going on. And there's as a first attempt, all their answers come to an automated system, and the system also needs to have its own confidence measurement. The system should not just know how to answer some questions; it should also know that given this input, I do not know how to answer it. So then that question gets forwarded to the actual class teacher in that case, so that the student experience is not hampered. So this is part of the rapid prototyping that even if your system is not 100% accurate, and it won't be when you're starting with it, you need to have a fallback, which can gradually reduce in its scope. So as and when your system keeps improving, the fallback chances and the number of times it is being escalated, that would reduce. So this is again part of the active learning kind of design framework, in which you start with a simple solution and you need to build on top of it. And it's in this paradigm of user generated data that will have a lot of ambiguity and uncertainty, that this kind of a paradigm is a lot more suited than what we are used to in research, which is having a more very robust problem formulation and trying to, in the first attempt itself, trying to make an elaborate model that incorporates all the nuances in the data. And of course that is something that we also try to do in production as well. But given constraints like computational cost and changing evolving nature of data, it's like a cat and mouse game, so which we also need to be agile in our development. So right. Okay, so yeah, with this, I have done a lot of talking. Any remaining questions? Let me quickly look at the chat panel. Oh, I think I'm sharing the wrong screen.
Yeah. Thank you, Mr. Anshul Babaji. Thank you very much. So, any questions from the audience? So, one of the participants want to know about any NLP-based mini project and available resources related to them that you may know.
Right, right. There's a website called Kaggle that has a lot of uh,
Yeah.
open data sets that are available. And also,
Mhm.
when you're reading any research paper, you can go to paperswithcode.com, and like there's you'll also find a lot of implementations, and it's not just like you see how they've done it, but yes, Kaggle. And with Papers with Code, you'll also be able to access their code, and you can pull it on GitHub, and you make changes there. And it's a lot. That's the best way to learn, in my experience. That uh, before making the full project yourself, you look at existing projects and go through them, and like try to figure out why things were done the way they were done. Otherwise, a lot of times it happens in research is like you get inspired by somebody's approach and you try to do it in a different way, but then you realize that the first approach doesn't work, and then you end up making the same mistakes that that person also made. So if somebody has done it, and in the paper, just if you look at the paper, they'll mostly talk about their positive results, like look, we got this, look, we got that. They may not talk about the process in which the negative results were also there. We had tried all these things, they did not work. And though that is important learning also, and this is something I feel that you know negative results should also be published, because you learn, because a lot of people have those similar ideas when they're starting, and it'll we don't have to reinvent the wheel every time. If somebody has made those mistakes, we can learn from their mistakes as well.
Very much true, sir. Very much true. So, any other question from the audience? Anything you want to ask from the sir? Okay, thank you, Mr. Anshul Babaji, for sharing your views about applying natural language understanding at scale. Definitely, there is a difference when we implement something at the lab level and when we implement in the actual scenario. A lot of systems just crash because when we try it in the real scenario. Your explanation about how we can apply NLU at scale open a new dimension for our participants, and I am sure that our participants definitely consider your points while doing the research. Thanks once again for sparing time for this session and joining us today. Thank you very much.
Thank you so much, sir, for organizing this.
Thank
It was a
you.
pleasure. Thank you.
So with this, we are now concluding the second day of